Okay, hopefully this won't take too long. Just to do with Earth and satellites and the adjustments that have to be made due to their different positions and velocities in a gravitational field. So first of all, for Earth, I'm going to put in a very small b value, which turns out to be to do with the orbital velocity, which I'll explain down the bottom. So there's going to be another b value for the satellite because it's in a different place. So we've got two b values. So first of all, on Earth, the surface of the Earth, the centripetal acceleration is m divided by s squared, and I showed above how to convert L and T into meters and seconds. Here it is, meters and seconds, and all you need is the scalar r and the constant c. So I've put in the radius of the Earth to the surface, which is about 6 million meters. So I've put it in there. Okay, and that's the centripetal acceleration, or we call it gravity, on the surface of the Earth. And just to compare it with the proper acceleration pushing upwards on us, it's basically the same value. You can see there, slightly more proper acceleration. Anyway, here's the Earth's mass. I have to divide out g because L cubed over T squared is actually gm, not just m. And that's in kilograms, 5.9 times 10 to the 24 kilograms. Okay, so what's the difference in the speed that clocks are running on Earth compared to the speed that they're running on the satellite? Well, first of all, the energy loss per second relative to a clock in flat space-time causes clocks to run slow. So in this case on Earth, compared to flat space-time, b squared gives you the amount of it's the energy loss per second, which makes the clock run slow by that amount per second relative to the flat space-time clock. Okay, now the time loss per day relative to a satellite is this calculation. I've turned it into days with the 86,400 number there. That's just turning seconds into days. And then I've taken the energy loss on the surface of the Earth, and I've subtracted off the energy loss on the satellite so that you get the energy difference, and the time difference is then this 38 nanoseconds, which is correct. 1, 2, 3, 4, 5, 6. It should be microseconds. Sorry. And space loss per day relative to the satellite is going to be that amount, about 11 kilometers, which is quite a lot. And notice that it's quite a simple relationship, and in fact the potential energy of the satellite is whatever b squared is, and the kinetic energy is half that, and it's due to the sideways boost that's been given to the satellite to put it into a stable orbit. So it's a tangential acceleration that has to be given to it, and that causes further time loss. So you have to take into account both potential energy and the kinetic energy of the satellite when you're working out the time loss relative to each other. Okay, finally, what is B? It's orbital velocity. So you just multiply B by C, and you can see that is the orbital velocity on the surface of the Earth. So in other words, if there was no air, something could go whizzing around at about 8,000 meters per second. It would orbit and stay up there. But on the satellite only has to be traveling at about 3,800 meters per second to stay up there, which is the B value times C. Yeah, that'll do.